Hello, here we go. Right now, girls, hold up, please. Here we go. Now, to begin, 14A, instead of just teaching you the skill, I'm going to get you to think about the overall thing. Because once you understand it, it should make much more sense of what you're doing, why it's called circular functions as well. Now, the first exercise, you're learning to convert degrees to radians and radians to degrees. The problem here is I can teach you the formula, I can teach you how to do it, but the problem is a lot of students don't know what radians is. And at the end of it, it doesn't mean anything. So I need you to understand what radians is, then it makes more sense what you're actually solving for as you're moving throughout the topic. So I want you to think about this. Back in years 7 to 9, your middle high school, this is a circle, okay? Let's say, if I told you the radius is 1, okay? We call this a unit. So this unit means 1. Now, I don't know if it's 1 centimeter, 1 meter, 1 kilometer, I don't know. But it's a 1 unit. Okay, so 1 unit by 1 unit by 1 unit by 1 unit. Okay, so I don't know what the units are. I just know it's 1. So we call this a unit circle. Now, if I asked you back in year 7 to 9, I asked you, what is the circumference of the circle? Again, what's the formula for the circumference of a circle? What would you tell me?
2 of those units times by pi squared.
Not squared. You were saying it? 2 pi r. 2 times pi times r. So 2 times the pi times the radian gives you the circumference. So this is your formula for the circumference, which means the perimeter or the outside length, right? So you said pi times d or pi times r times 2. Because diameter times 2 is the radius, right? So this is going back to year 7 and 9, finding the circumference, which means the distance around the circle. That's why I need you to understand, because that's what radians is. Radians is actually the measure around the circle. Okay? It's different to degrees, and a lot of students will confuse the two there. So now let's think about it. If my radius is 1, then what's the distance or what's the perimeter around the circle? Think about it. If my radius is 1, you told me to find the circumference or find the perimeter around the circle. You told me it's 2 times pi times r. Now, if I told you the radius is 1, then the circumference has to be 2 pi. Because radius is 1, then the circumference is equal to 2 times pi times 1, which is 2 pi. Okay? Now, this fact here, we know that in a full circle, yes, the distance is 2 pi in a unit circle. But not only that, we also know that if you did an angle of full revolution, we know that the angle for a full revolution is also 360 degrees. So what we can say is, in terms of 2 different units, one's measuring an angle, one's measuring distance, we're saying that 360 degrees as an angle is equivalent to, in terms of ratios, is equivalent to 2 pi distance. Does that make sense? Have I confused anyone? No? Because this is where the whole shebang comes from 14A. Okay, it just comes from this idea. Unit circle, radius 1. Circumference is the distance. So radians, this is called radians. Radians is the distance around the circle. Degrees is the angle that it makes. Okay? So you can go around the distance of the circle. Think of it as like a lap. You can run around like 2, 3, 4 laps. Okay, so if I did 4 pi, because if 1 lap is 2 pi, then 2 laps would be 4 pi. 3 laps would be 6 pi, right? Degrees, on the other hand, will be different. 360 degrees plus another 360 gives you 720. You add another 360, 180. Good. So, what I'm trying to say is the ratio that you're working with, this is an angle, and this is the radian, which is distance. It's the outside length. Don't forget that, okay? Now, using this property here, 360 degrees is equal to 2 pi, okay? Then what we can do now is we can start to break it down to 1 degrees and figure out how much it's equivalent in terms of radians. Because we don't know how much 1 degrees is equal to. We know that 360 equals to 2 pi. Then if I asked you, how much is 1 degrees equal to? Now let's go back to what we learned back in year 7 and 9. We can convert 360. How do I change 360 to 1 degrees? What would I have to do? Not minus, because we're keeping ratios here. Divide 360, we're keeping fractions. It's like saying, when I say ratios, ratio is like a fraction. I'm just saying 360 degrees by 2 pi. So if I want to change this to 1, you would have to divide this by 360. And that means I have to divide the left-hand side also by 360. Now this will give me a ratio. 2 pi on 360 will tell me to know what 1 degrees is equivalent to. It's 2 pi on 360. True? Now if I reduce this fraction, 2 pi on 360, what does that simplify to? 1 degrees is equivalent to what? Simplify over that fraction.
80 on pi.
80 on? No.
Pi.
Pi on 180. Okay? So if you think about it, divide top and bottom by 2. If you divide top and bottom by 2, divide this by 2, divide this by 2. I'm just doing fractions right now. That becomes pi, 360 divided by 2 is 180. What I'm saying is 1 degrees is equivalent to pi on 180. Now this is nice because that's the first rule. And I haven't done anything. I've just taken this property, okay? I've just taken this property, I've just rearranged it so I can find out what 1 degrees is equivalent to. And I just figured out that 1 degrees is equivalent to pi on 180. So that means if I want to find 10 degrees, okay, if I want to find 10 degrees, if I know 1 is pi on 180, then how do I find 10 degrees? What do I have to do from 1 to get to 10? Times by 10. Because that's the logic. If I have 1 degrees is equal to pi on 180, then if I have 10 of these, then I have 10 degrees. True? 10 degrees, 1 times 10 to get to 10. That means on the right-hand side, I times this by 10 as well. So I'll be saying pi on 180 times 10 will give me 10 pi on 180. But if you simplify that, that becomes pi on 18. So when they say convert, if they say convert degrees to radians, right? I've just done that. I've just done 10 degrees. How do I change it to radians? I just did times by pi on 180. That's what I did. I did 10 degrees times pi on 180. That gave me pi on 18. So pi on 18 is my distance. The reason why a lot of students find radians difficult is because they don't know what pi on 18 means. Type it in your calculator. Pi is about 3.1452. Divide that by 18. That's the distance. So this means distance. This means degrees. So logically, on a unit circle, what are you actually doing? This is what you're saying. You're saying if I made 10 degrees increase, the distance from here to here is about pi on 18. That's what you're saying. That's what it means when you're converting degrees to radians. You're just saying, when I have 10 degrees in the unit circle, 10 degrees, the distance, so the distance around the circle, you said the distance for full revolution was 2 pi. Well then what if I have 10 degrees? 10 degrees is pi on 18. It just tells me on the outside distance is pi on 18. So if I halved it, if I said 180 degrees, see if 360 is 2 pi, then what's 180 degrees? Pi. So that means 180 degrees is half the circle, half the distance is pi. So if I did pi plus another pi, well, it makes sense. It makes 2 pi. That's why 180 plus 180 is 360 degrees. But you have to understand that radians is the distance, degrees is an angle. They're two totally different things, but they're useful in their own areas. You can either talk about distance in terms of a worded problem, or you can talk about angles to sort of picture like how far you're angling a particular incline or whatever it is. Okay? So what I'm trying to show you in the very first exercise, they give you two formulas. They give you how to convert radians to degrees and how to convert degrees to radians. I don't want you to memorize that, because a lot of kids try to memorize that, they get it confused. They're like, is it pi on 80 or is it 180 on pi? Which one is it? You don't need to memorize it, because this is all you need to know. 360 degrees is equal to 2 pi. So if you want to know degrees, work out from 1 degrees. If you want to know how to change radians, work out from 1 radian. Now let's think about it. Same drill. If I want to find out for 1 radian, I'm just going to use an eraser here. If I want 1 radian now, okay, I'm going to do it in red here. Instead of 2 pi, what if I want to know 1 radian? Now notice I'm using a C. Whoops, sorry. C, right there, that's called radians. That's the symbol for radians. Okay, so with a little circle there, that means degrees. Little c means radians. So we're now talking about distance. How do I go from 2 pi down to 1 radian? What do I have to do? It's a ratio again.
Would be, if it's 2 pi, that would be over 360 degrees. 360 degrees over 2 pi.
Yes. Okay, because in this case here, how do you change 2 pi down to 1? Just 2 pi divided by 2 pi. Divide itself and you get 1. So here, if I said divide this by 2 pi, and I divide 360 by 2 pi, I will get how much, degrees would, how do I convert it? It's 360 degrees over 2 pi, but if you really simplify that, 1 radian is equivalent to 180 on pi. This is your second formula. See, there's two formulas that I've just given you. One was, how do you change degrees to radians? Times the degrees by pi and 180, and you'll change it. Or, look at this, how do you change radians to degrees? You times all the degrees, all the radians by 180 on pi. And it solves the issue. But these are the two formulas, and I don't want you to memorize it, because it all came from here. It was just 360 degrees. 2 pi is the distance. Why is it 2 pi? Because radius is 1. Because we're dealing with unit circles. That's why you don't need to memorize. Yeah? And everything that we're going to do, Sokotoa back then as well, all comes from a unit circle. The better you understand this unit circle, the easier it is for chapter 14. Okay, now I've successfully taught it to my year 12s and they totally understand circular functions. I'm hoping they're doing the same for you guys. The better you can picture the unit circle in your head without trying to memorize Sokotoa or ASTC, don't worry about all that. Those will take long to understand, a lot to memorize. I'd rather you get the unit circle. So if you just remember that property, 360 degrees makes sense. Full revolution, 360. Distance around a circle, 2 times pi times r, but r is 1, it's radius 1. That's why it's 2 pi. From here, you can derive those two formulas. Okay? So you got two formulas here. You just got how to change degrees to radians and how to change radians to degrees.
1 radian.
Okay? All right. Now, let's do an example just so that you feel a bit more comfortable with it. So if you didn't like what I wrote there, this is the printed version. I'm just showing you half the distance, 180 degrees is pi, half the distance, half of 180 is 90, then you get pi and 2. Okay, so this now, that's what pi and 2 looks like. And that's how I worked out 1 degrees is pi 180. And this is how I worked out radians, 1 radians, 180 on pi. Okay? Now, let's use these two formulas to answer the question. Let's try this one. 30 degrees to radians. Now remember, we just figured out before 1 degrees is equal to pi on 180. So if I want to know 30 degrees, how do I convert 30 degrees? What do I do? Multiply by what? Good, multiply by 30. So this is all I'm doing. I'm just going to say multiply pi on 180 by 30. See, because I'm multiplying this by 30, I'm also multiplying this side by 30. So 1 to get to 30 times 30. Type in your calculator, that's 30 pi on 180. So 30 degrees is equal to, now 30 and 180, reducing that fraction. How do you reduce 30 and 180? What does that become? Pi over 6. So 30 degrees is pi and 6. But don't get confused by the pi. We're just simplifying. We're just writing an exact value. All it's trying to say is in a unit circle, when you make 30 degrees, which is about there, it's not 45 degrees, let's say 30 degrees, then the distance from here to here is pi and 6. If you want to know that as a decimal, then, type in your calculator. We go to your calculator and you just do pi divided by 6. That's how far you've gone. 0.5235 units. We just don't know what the units are. It could be centimeters, could be meters, whatever it is. But all I've just figured out is that is 0.5, what was it again? 2359 units. That's all I know. That's the distance on the outside. Okay? Yes?
In the textbook, it has it written as pi radian over 6. Do you want us to write answers?
No, later on you won't use the C. Like people will know if you write pi and 6, it's a radian. Okay. It's just at the start when you're learning radians degrees, they're just putting it so you can tell the difference. Yeah. But later on you don't need to put the C. Okay? So that's what I'm trying to describe to you. Just try to understand the unit circle perspective. Degrees is the angle that you make. Distance on the outside of the circle is called radians. That's what radians is. Okay, so even though it looks hard, it's not. And the reason why students don't like circular functions is because we deal a lot with fractions. And students generally aren't really good with fractions. That's why circular functions is one of the hardest ones to pick up. Because if I start talking a lot about fractions, people are like, oh, can't picture what he's talking about. But I'll show you why we like radians. Actually, I'll show you right now why we like radians. radians is easier or nicer to work with than degrees. Even though you feel that degrees seems more like it makes sense at the moment, radians is better. And I'll show you why. Radians is better when you move multiple circles. So if I did one revolution, you all know that was 360. True? Okay, but 360 degrees, so that's one revolution, 360 degrees, we make a distance of 2 pi. Now, if I told you I went 9 pi, okay, you can roughly figure out where I've gone, okay, because if 2 pi's are here, think about it, I started at 0, I went all the way here, that was pi, then I went here, that's 2 pi, now I go all the way here, that's now 3 pi, and I go all the way back, that's 4 pi, okay? Now I want you to think. This is, the pattern here is every time I land here, it's pi, 3 pi, what's the next one? 4 pi. 5 pi, all the odd pi's are here. All the even pi's are here. See, 0, 1, 2, 3, 4, 5. So if I had 9 pi, where should I be? Over here. Okay. But if I asked you now, how many revolutions was that? You can still work it out too. You can say, well, how many 2's fit into 9? About 4 revolutions. 4.5 technically. But if I asked you now, tell me the degrees for it. How many degrees will be, what's the degrees for it? We know 1 revolution is 360, we know 2 is 720, and we know 3 is 1080. Then what's the next one? You keep adding 360, it's much harder to work with. And it's even harder if I asked you now, if I wrote this number now. So if I changed this whole thing and I said, what is 3,125 degrees? Where am I? See, that's hard. You're going to sit there and you go, I'm going to have to divide it by 360, figure out how many revolutions I am. Then you can have an idea where you're sitting at. Whereas if I wrote, let's say, 12 pi on, let's say, actually 12 pi on 5, okay? You can convert this. You can convert this. 12 pi on 5 is the same thing as saying 2 pi's with an extra 2 pi and 5. True? Because there's 2 holes. Think about how many 5's within 12? 2 holes with an extra 2 bits. At least you now know 2 pi is 1 revolution. 1 revolution with an extra 2 pi and 5. At least you have an idea it's 1 revolution. Whereas degrees, if I asked you 3,125, it's tricky to know. That's why we work with radians. Radians is easy to tell where in the unit circle I am. Degrees is much harder if you start doing many, many revolutions. Okay, yes, Finn?
How does that happen? Like, you just get rid of 360?
Say it again?
You just get rid of enough 360.
Yes, you could. And you could do it that way. It's just that it will become much more difficult, especially if I did 10 revolutions. Then that means you now have 3,600, right? If I did 20 revolutions, that now also increases the number. So when you do sine, if I said, which you're going to learn Sokotoa, if I asked you to do sine of, let's say, 20 revolutions, you would now have what? That's 7,200 degrees. That's what you'd be typing. As opposed to, if you did 20 revolutions, okay, in terms of pi, it's easier to read by just writing 200 pi. See what I mean? And it tells you exactly where you are. And if I changed it, if I wrote 721 degrees, that's also even harder to figure out because 7200 was something familiar. But if I chose 5,960 degrees, then where am I? Where am I in this unit circle? Am I in this quadrant, this quadrant, or that quadrant? That's going to be tricky. Whereas if you do it in terms of fractions, fractions is easier because you can either have one whole, you can split into the quarter, you can say I'm between this quarter, or you can say I am in this bottom half. It's easier to work with fractions as a whole number as opposed very increasing numbers of revolutions. That's why we go with radians as opposed to degrees. Okay, it'll make more sense when I go to when we start doing ASTCs and whatnot. Okay.
So this is still 14A, right?
This is still 14A. All right, here we go. Now, I converted 30 degrees to radians by multiplying pi and 180 by 30 degrees, and you told me the answer was 30 pi and 180, and the answer was pi and 6. Yeah? Now, how do I convert pi and 4 radians to degrees?
180 will multiply by 180.
Very good. Because we knew from before, we already knew that 1 radian was equal to 180 degrees divided by pi. So that means 4 pi radians. I would have to multiply this by pi and 4. That means I need to multiply this by pi and 4. And what you can see is pi on 4 times 180 on pi. Pi's cancel out. 180 on 4. That's what? 445. There you go. 45 degrees. Okay, so I'm just giving you two formulas. That's 14A. How do we feel? Pretty good? That's 14A. So all you have to learn from 14A is how to convert degrees to radians and then radians to degrees. You also have to know how to do this on a CAS. Okay, now I'm going to show you how to do it on a CAS. If you have a CAS, take it out. Or if you don't, write your notes for CAS here. Here we go. How do you convert radians to degrees? Let's say I chose pi and 6. Let's change radians to degrees. You see that catalog book over here? So you got a 9, your common functions you use. The little book over here, DD. So if you don't have that on your page, if you tap the letter D, tap the letter D and it will come down to this point here. Okay, then you can scroll down, up and down. This will change to degrees. Okay, so arrow DD will tell you what it is in degrees, and it's 30 degrees. If you want to change degrees, thanks, Finn. I'm just gonna make a pointer here, Finn. You know how you complain about not knowing how to use a CAS in the SAT? When I go through it, I've spent 4 sessions this entire year, and you complain that I can't do this, I can't do that. I'll tell you why. Exactly these moments when I do spend a session fully on CAS, and you don't follow what I'm telling you, and then you complain. That's what I hate. Now I told you guys, if you don't do the effort, don't complain. But if you start complaining, I get really pissed off. Because I'm doing the time, I spent 4 times this year, 4 times I've dedicated 45 or 50 minutes to teaching how to use the CAS. And a lot of you in that SAC, when I'm looking through that SAC, I can tell you don't know how to use a CAS at all. That tells me that you're not going home to practice that. And when I do show it and I do record it, you're not practicing yourself. So when you complain, that pisses me off. Don't complain. If you're not going to do the work, then don't complain. If you can't do that SAC and you're like, I don't know how to do it on the Windows, then that's your problem, not mine. Don't complain. That really annoys me. If you're not willing to put in the effort, don't complain about it. You deserve every mark and every decision that you get. If you did put in the effort, then you should know, because I've already covered that. And now I'm trying to cover this while we're doing the exercise so that you don't complain. So work with me. That's what I'm trying to say. So here we go. I've shown you how to change radians to degrees. Now if you want to change degrees to radians, in your books, same thing. Now it's going to be R. So on your calculator, press the letter R. Go to letter R, and you scroll down until you get rad. Rad for radians. If you enter that in, 30 degrees, change to rad. That will change it to radians for you. So it's pi on 6. So I'll go again. So you go to book. So it doesn't matter what if you press A on your calculator, see the keypad down here? If you press the letter R, it won't show up radians, but then you press up and down on the cursor. So you move up and down until you get to rad. Yep. You're pressing rad, and that's how you get rad. Okay? So you got that. That's exercise 14A. So what I've just shown you there allows you to change radians to degrees, degrees to radians. Now that's only important when you start doing applications. Okay, when you do applications, sometimes they want you to change radians to degrees, degrees to radians. Okay? You'll find that most of the questions you won't need to do this. It's just more of learning how to use the CAS. Okay? Now, today's lesson, it's not to do 14A. These questions you can now do with the 2 formulas, so you can do it as much as you want. I wouldn't suggest doing a lot of these questions. Okay? What I want you to do, and I told you at the end of this session, my goal is that your homework when you get home is to learn these times tables, yeah? It's called exact values, and I'm going to show you my way that I've taught my year 12s and every other year I've taught, and they can memorize all 15 exact values. You have to know all these exact values, otherwise you can't move forward, okay? I'll show you this method. If you don't like the method, you go on YouTube. There's a lot of other methods too, okay? Yes, my finger method. All right, here we go. Yeah, that was quite fancy. Wow. Here we go. These are the 15 tables that you need. You've got 5 special angles. 0, 30, 45, 60, 90 degrees. Those are your common angles, and it's all within the first quadrant. 0 degrees to 90 degrees. 0, 30, 45, 60, 90. Okay? You've got your three functions you learnt back in year 9. If you type in your calculator sine of 0 degrees, which is sine of 0, it will give you 0. If you do sine of 30, it gives you half. Sine of 45. These are called exact values because we know it's exact value, right? And there's 15 of them, and you must know them because without them, you can't do C, D, E, F, which is the Secretary of Public Law. So you need to know this like your times tables. When I ask you sine of 60, cos of 60, you have to be able to know them. So either you sit down and you memorize all that, or you go on YouTube and there's other ways to memorize this as well. I'm going to show you my way. That was my hand back in, I think, 2013 when I was looking inside some calluses there. But, I don't have that anymore now. Smooth that. All right, here we go. So, 0 degrees, your fingers here, now you don't have to be a left hand or a right hand, it doesn't matter. It's just from left to right. Okay, left to right, so I want your hands up. Look at your hands up. From left to right, the smallest angle is on your left. As you move towards the right, it increases. So 0, 30, 45, 60, 90. Okay? What I've wrote there is the radian version. Okay, so the radian version. 0 radians times 6 is 30 degrees. Pi 4, which is your 45, then pi 3 is 60, and then pi 2, which is half, like a quarter of pi. Also half of pi, which is 90 degrees there. Okay? Now, in the center, notice I've got sine and cosine. Sine is on the left, cos is on the right. Now, you might be like left of what and right of what? Just wait. And then the formula. Now, this is what I want you to copy down. That formula there will work and will allow you to memorize within an instant. Verse 10 out of 15. Okay? The formula is square root of something divided by 2. Now, how this works, if I want to do, let's say, sine of 30 degrees. Okay? So you ask yourself, which finger represents 30 degrees right now? Well, my finger, actually. The index. Okay? So 0, 30 degrees. So I'm going to drop down to 30 degrees. Now I said sine is on the left. Cos is on the right. In my case now, I'm doing sine. So sine, how many fingers do I have on the left? Because sine's on the left. How many fingers do I have on the left? 1. Now sub that into the formula. So that is now square root. Sine, which is the left, I've got 1 finger divided by 2. Now root of 1, which is 1 divided by 2, the answer is half. Now that's true, because I do have half. You can do that same thing with cosine. Let's say I did cosine of 30 degrees. Same thing. Let's do cos 30 degrees. Yes, you got 5 fingers, including thumb. Okay, let's go with the same thing. Cos, drop down to 30 degrees. Cos is the number of fingers on the right-hand side, because sine is on the left, cos is on the right. So in this case here, how many fingers do I have on the right-hand side of the 30 degrees? 3. So in my formula, I would sub 3 in. It's square root of 3 divided by 2. And that is true because cos of 30 degrees is root 3 on 2. Okay? Let's try another one. Let's say I did sine of 90 degrees. Sine of 90 degrees. Same thing. Which finger is my 90 degrees?
The pinky.
The pinky. So I'm going to drop down the pinky. Sine is the number of fingers on the left of that pinky. So I've got 4. So the formula says square root of 4, which is 2, and then 2 divided by 2, which is 1. Okay, so I'm going to write it down again. Root of 4 over 2. Okay, good. All right, so here we go. So that one tells you one that's true as well. So let's try 45 degrees now. 45 degrees. Now if I do sine of 45 degrees, okay, which finger is 45 degrees? Middle finger, so I drop it down. Now sine is the number of fingers on the left of 45. How many fingers do I have on the left? 2. So your answer will be square root of 2 divided by 2. Now we don't know what root 2 of 2 is, so we leave that as an exact answer. Now I know it looks different to 1 on root 2, but why do you think it's different? They're equivalent. Why is it different? What have I done? What have they done there? But technically it's still the same answer as mine. Why is 1 on root 2 the same as root 2 on 2? It is the same. What's the change? What's the change? This is specializing, rationalizing. When you learned it in I think year 8 or year 9, rational numbers, how do you rationalize the denominator? That's an irrational number right now. How do you make this a rational number? You would? Yeah, multiply top and bottom by root 2. So you're still keeping it the same ratio. But if I multiply the bottom by root 2 and multiply the top by root 2 times root 2 is 2. 1 times root 2 is root 2. Okay, that's called rationalized denominator. But if you left your answers root 2 and 2, it's fine. Nothing's wrong. Okay? Most of the time you find that you might have to convert to root 2 and 2. Okay, because it cancels out nicely with, if you doubled it, it comes root 2. Okay? So either one is fine. The answer is root 2 and 2 or 1 and root 2. They're both the same thing. One is rationalized denominator. One has a rationalized denominator. That's it. Okay, good. So, the formula I taught you, you can find this on YouTube. Okay, this one is on YouTube. Square root of the number of fingers divided by 2. That's on YouTube. So even if you forgot it, you can still watch it. But this one I made up. This one I'm pretty proud of. Okay, for tan, I made up this formula because I was trying to figure out how it works and I was thinking backwards. And it just works out. So here we go. For tan, everything else is the same. Still 0, still pi 6, still pi 4, still pi 3, still pi 2. Formula changes. Now we know tan back in year 9, when you learned it, tan is the same thing as saying sine divided by cosine. Yes? Yes. Okay. So that means the only difference here is still the square root, but this time you square root the entire thing. It's the number of sine fingers divided by the number of cos fingers. So let's do an example. Let's say I want you to find tan of 30 degrees. Which finger is my 30 degrees again? Index finger. Drop down the index. So, according to this formula, number of sine fingers I have 1. Number of cosine fingers 3. So it's 1 divided by 3, and square root all of them. Square root both of them. So, if I write it down, square root of 1 over 3. Now I can split that up into root of 1, root over 3. Now what's root of 1? 1. What's root of 3? We can't. So the answer is 1 and root 3. Which makes sense. Tan of 30 degrees is 1 and root 3. Yes, Ian?
You took exam, right? If you like mess up, then you'll be also.
Yep.
I mean, if you mess up, then you'll be also.
Yes, you are. Totally. Every digit or square root, whatever you do wrong for circular, yeah.
Wait, is it on no cast?
Yep. Yep.
So just before the sap, write out.
Yeah, you could write on your hand. Yeah. All right, let's try tan of 45 degrees. Same thing. Same thing with tan of 45 degrees. Tan 45, which is which finger again? Which finger is 45 degrees?
Middle.
The middle finger, right? Drop it down. Now the formula is number of sine fingers divided by number of cos fingers. So how many sine fingers do I have? 2. How many cos fingers do I have? 2. So 2 divided by 2 is 1, and then square root that answer. 1. Makes sense. Tan of 45 is 1. Okay? I want you to learn this formula. Now, let's check why tan of 90 degrees is undefined. Let's check that. Tan of 90. Tan of 90, this is my pinky finger. Number of sine fingers. 4. Number of cos fingers. 0. But we know that every time you divide 0, that's why it's undefined. If you do it the other way around, tan of 0, it's okay. You got 0 divided by 4, it's okay. Your homework over the weekend is that I want you to learn that, because when you come into the next session on a Monday, I'll be testing you. So without a chart, I'll be calling out your name and I'll say, what is tan of 60 degrees? I'll say, what's sine of 30 degrees? What's cos of 45? You have to know. Okay? This is now 14C. This is 14C, exact values, which leads to D and E. Okay? That's what I want you to learn. Over the weekend, learn that table. Learn that table. I don't care how you learn it. That's my way. Okay? You've got the hand method. Okay, and I know which students are my students because you look in the exam and you see kids doing this all the time. And you know, you're like, oh yeah. All right, I'm going to stop there.